The following content has been provided by RWTH Aachen University.
All right, then welcome everybody to iOS application development. Last time, yesterday, you had a look at things like table views, etc. And today we're going to cover a whole bunch of things which all build up in order to be able to write apps that talk to the web. So to get out there and collect data from web servers, talk to web APIs, display online content, etc. To get there, we will first look at how to save data locally, because that's one of the things that, of course, you always need to do when your user is working with your app. They expect stuff to still be there next time they launch it, anything they entered. And then we will look at closures, a very elegant swing language construct that lets you work with functions as values in expressions. And you'll see how that actually gets used in Swift and in UIKit quite heavily. We'll take a look at animations because they make your user interface more smooth, more fluid, and better to understand. And they also use closures as a language construct. And then we'll take a look at finally, JSON, working with the web, etc., where all these things come together. So it sounds like a mixed bag, but these things actually all build on top of each other. So let's start with saving data. This, by the way, if you want to catch up on this, read more details, is also covered in the data collections book, the Xcode 13 edition, in lesson 1.7. It's like page 161 following. This is where you can read on with this. We've compressed it a bit and adjusted it to your level, which means it's a little bit more advanced than how the book approaches it. So since you need to at some point store data, save your user's work, we will talk about, first of all, a very simple approach to do this. Essentially, you take an MVC model, right? From your MVC paradigm, you've got your model data, and we will talk about how to dump that into a local file. We'll use the codable objects for this, and more advanced storage methods will be covered actually in the seminar. One of the things in there, SQLite and core data, these kinds of things will come up later. So how do you encode and decode with Codable? You basically, you've seen Codable before, right? We've actually talked about this before. And if you have an object that conforms to the Codable protocol, you can have an encoder object that encodes what's inside this thing that is conforming to the Codable protocol, and then basically gives you a data representation of that. So what happens is that the encode method of an encoder, returns something called a data object, right? And this data object is something that then the decoder can take later and unpack again. Data itself is a Swift structure that basically represents data just stored as bytes, right? So it's an unstructured form of doing this. So what we're talking about right now is how do you move between a Swift object that is part of your model in your app and basically a byte string, right? That is the data type. Once you are at the data type, once you have this byte stream, then you can actually dump that into a file or read it from a file, right? So you need to first go from your object into an unstructured bit stream, essentially, and then you can take that and dump it into files. What we will be doing is we will actually be encoding our object that we have in our example here into a plist. Plist is short for property list. It's a very simple format of storing key value pairs. Settings for apps on iOS and macOS, for example, are also stored in plist files. So it's a very common dictionary style format. Now, as you may know, maybe we can take a look at this here in an example. We'll take an example of, let's say you're writing a Notes app, right? Where people can write down little snippets of text and store them, like the built-in Notes app in iOS. So you might have a struct that defines your model object, right? Could be that a single node is represented by a title and a text, which are strings, and maybe there's the timestamp of the data type, okay? In order to make this codable, so in order to make this so that you can turn it into a data object, and which means that you can then store it to a file, you basically have to, hit 7 keys, right? You have to just say conforms to codable, and you're done. Why? Because Swift auto-generates the encoding, decoding logic that is necessary for this. If, anybody know why that works? Why do we not have to basically write anything except for saying, oh, conform to codable? Yeah.
Maybe because all the properties are also codable?
Exactly, right. All the properties are also codable. So Swift can auto-generate that for us, right? And if Swift can auto-generate it, it usually does. It tries to make your job as easy as possible in that respect. Now, in this example here, we're creating a sample node called myNode with some text for the title text and timestamp. Timestamp is just today's date. If you just use the initializer here, it'll fill that in. And then what we do is we actually create an encoder. Right? The property list encoder is a particular type of encoder that encodes data into what's called a property list. Right? So property lists are dictionaries of key value pairs. And then what we need to do is to actually take that property list encoder and tell it to encode the data structure, right, my node. And if that all works out, as we can see, we have to do a little bit of extra magic here because the encode method is actually a throwing function. Right? So since it is throwing, we have to use try and what we get back is an optional essential data format there. We could also do a whole do, try, catch structure here if we wanted to, but we'll keep it simple. Right? So once we've done that here, this print statement would simply just return basically 130 bytes if you actually ran that, because that would be the length of the encoded node. Now, if we take a look at how to decode this kind of stuff, we would say, okay, we now actually have an encoded node, right? So let's take the encoded node and stuff that into the decode method of a property list decoder, which we here create. Again, it's one that will return optional values. So it can fail, right? That's why we need to run it in the try. And once we do that, we get back a decoded node. And if that is successful, we could print that out. Now, so that means that the second one would actually output a node object. Right? It would basically output the node object similar to the one that we created here in myNode. So if you ran that in a playground, for example, I encourage you to try this out. You would see that the second print statement properly decoded the data back from the byte stream into something that you can read and that basically has the structure of a node again. Whereas here, this first print statement would just tell you 130 bytes or something, because it's basically an unstructured data that is, however, ready to write to disk. But we haven't written anything to disk yet. Right? This is not persistent yet. We haven't stored anything yet. We've just moved things between the normal object and a data stream. Anything else in here? Yeah. So the decoder kind of has to do some magic, right? It gets a stream of bytes, and it's supposed to create something from it. It needs to know what to create, right? It needs to know, okay, what should I make from these bytes? And so that's why you need to tell the decoder with note.self, you tell it whatever you're creating there will be an object of type node, okay? So we're passing in the node type here. Node.self with the capital N, this is the class, right? Or the struct in this case. Node type .self means that we're passing in the type of node here to tell it basically, this is the blueprint which you need to fill in with the data stream that's coming in that is completely unstructured. All right, so this is how we can encode and decode with codable protocols or objects that conform to the codable protocol. Now, what about actually saving this to disk? I'm sure, as you know, saving to disk isn't as easy as it used to be, right? Back on old school desktop systems, you could say, put it in this folder, directory, whatever, on your Linux system, for example. You could just dump stuff pretty much anywhere. Well, there may be some file, permissions that are set this way or another, but apps usually could do pretty much anything they wanted. And this is not the case on modern mobile operating systems, as I'm sure you're aware. When your app is running on a device, it basically cannot access data outside what's called its sandbox. Right? So it's basically running inside the sandbox, which means that anything that the app can access is only its own files, its own preferences, its own folders. So this blue app here running in sandbox 1 can access its own data. The green one can access its own data, but they can't actually easily get to each other's data. How do they get to each other's data? What needs to happen for them to actually be able to reach outside the sandbox? Yeah? Exactly, right? The user needs to say, yes, it's okay for this app to actually access, let's say, your contacts, for example. So normally we stay in there. Now inside this sandbox, apps on iOS have a variety of standard things. For example, a documents folder. And this is a good location to put data that is related to your app, right? For example, if the user in our Notes app started adding notes that they wanted to keep, you could put that in there. And the access to this folder, however, is a little tricky. Right? So let's start with this. You might think, oh, I'm just going to say, I'm just going to put this into /documents or whatever it is in my sandbox. But this is not how it works. There's another security mechanism which actually makes it so that each time you launch your app, the actual path that leads to your documents folder for your app is different. It has some long random string in there, which is basically a security precaution so that this actual file path cannot be accidentally or maliciously shared with others who could then basically try to circumvent the sandbox. So how do you get to your documents folder? Well, you ask what's called the file manager. The file manager will actually give you the path to the documents folder correctly. This is inside the Foundation framework. Since that has nothing to do with the UI, right? This is an underlying basic functionality. So what we do here is we first get the documents directory, right? So we ask the file manager for the document directory, and from that on, we basically then say, okay, inside the document directory, I would like to create a file that is called notes data, and I want it to have the extension plist. Right? And just instead of saying .plist or something, we actually semantically tell the system to use this path extension. That's just to avoid confusion. You might have like two periods in there, like .xz, .yz, and so this way you tell it which extension you actually mean for this file to be used. So the result of this would be when we do all this, we would have an archive URL. This archive URL is a long string that has a lot of gibberish at the beginning, which is the mangled sort of path that moves towards your document folder, that changes each time, and then /documents /notedata.plist. Okay, so let's assume we have this. Now we know how to basically get to where our file is going to be, right? Where we want to store data. Now we want to write some data to it. How do we do that? You will actually basically use the code that we already had, right? So you'll have your property list encoder. You'll take your node, you encode it, and once you're done with that, the encoded node actually supports write. Like I said, this data type here actually supports writing and reading from and to files. So we write to this URL, and there's a couple options you can use when you issue a write statement, like don't use any particular file protection for this, like a read protection, for example. Sorry, a write protection. Later on, we can then read this file, and so now we've actually stored something on the local device, right, in this folder. And later on, we could load that again, right? Somewhere else in our code, we could have the stuff that we already saw, right? So the retrieved node data is now coming out of a data object, and that data object is instantiated here You can see we're using the initializer with contents of archive URL. So essentially, you can tell the data object here, or the initializer for data, simply to take a URL, which is this complete long path, and build up the information from there. And then the decoded node basically comes out of that by the same line that we've seen before. All right, so now we've stored stuff. Now, that's not a very useful nodes app because it only stores one node, right? But the nice thing about this mechanism is that if you wanted to store a whole array of nodes, go ahead, right? Hardly anything changes. If instead you had created a whole array of nodes and you had done the same thing with that array, the same thing would have worked. Because again, an array of things that are codable is also codable, right? Like you said, you just don't, as long as the underlying data structures are codable, it works automatically. Now, of course, if you were doing this in a real project, you would typically make your model objects codable, right? If you think about MVC, your model objects are typically the things that you may want to store out to disk. And then you got a couple options on where you put your save and load code, but a typical approach or a common approach is to have static functions in that are called like save file to disk or load data file from disk. These would be methods that are statically defined in your model. And then you load, for example, well, actually, when would be the first time that you load your data? Anybody would know where would you hook that in your iOS code? What point would you use to put your loading function? Yeah.
Maybe the app delegate?
The app delegate is an option, exactly. You could also put it in view did load, right? So because that's pretty much also one of the first moments that you are actually given the chance to do something on your own in your app. So it's pretty easy to do that. And when would you save? When would you issue a save? Yeah.
I think the app delegate tells you when the app enters the background. So
exactly. Right. So the moment you are pushed into the background is a really good idea to save data. But of course, you can do that more often, right? Whenever somebody changes your model code, you can decide to save that to file if that's what you want to do. And since the whole handling of files, especially in smaller apps, I mean, not in things like large desktop-y apps, right? Stuff like numbers or so. But all the smaller apps don't really have the sense of saving and loading files anymore, right? It doesn't work that way. It's an app-centric design, not a document-centric design. If you think about how people interact with these mobile devices, so they don't think about saving stuff, right? They just assume that this stuff is persistent every time they pick it up. It's supposed to be there again. All right, so much about how to encode, decode, and save stuff locally. That's part one. Now, a little intro into closures. Closures, this you'll also find in the book if you want to read up on this, is lesson 2.1. Starts on page 315. And what we want to understand about closures is that they are one of the the big ideas, right? Because closures are essentially code blocks that you can pass around as a value or as a parameter, for example, and then they get executed later. They're kind of like functions without names, if you want to say it that way, that you can store in variables or that you can pass as arguments. They're also sometimes called anonymous functions in the literature. Any Kotlin developers here? What are these called in Kotlin? Any Android folks? Any guess? Come on, take a guess. What do you think?
I really don't know.
No? Yeah, I heard lambdas. That's what it is. It's actually lambdas. And they're like, yes, that would have been my answer. Okay, so lambdas in Kotlin, that's the same thing, right? And you've probably heard about lambda functions in theoretical computer science too. So the big idea here is the following, and this is something I want you to pay close attention to because that's important no matter whether you're doing Swift or other languages. In traditional languages, it was actually functions were not first-class citizens, right? You could put a value like an integer or something into a variable, or you could put an object into a variable, but you couldn't take a function and put that into a variable, right? Functions were not values. You couldn't pass a whole function around as something to do stuff with. This was just not a concept. There was a very weak, sort of hacky way to do that in old C style languages. Anybody know how that would work, and if you really had to go down to a level of C? Yeah? Function pointers, exactly, yeah. And function pointers are essentially just memory locations, like addresses, and then, you know, that's where the code is to execute that stuff. But it's not very safe. You can mess things up in glorious ways with function pointers. And it's not a very good abstraction of the concept. So modern languages, like Swift or Kotlin, have this idea of these functions being able to be first-class citizens. And that's an important concept. We will actually need these to talk to the web. For example, you may have to tell UIKit that you have some code that needs to be executed once a piece of data has been loaded from the web. So you have some code, and that needs to be passed essentially as a value into some other method to use it once the data is there. Right? That's one example. But we'll also see that we will use this in collections a lot. In fact, we talked about map, filter, reduce recently, right? And map, filter, reduce, that's what are you doing there? Well, you're telling the map method or the map function, please do the following on every object in the array, right? Or in the collection. Well, do the following, that's specifying essentially a function as an argument, as a parameter in a call, right? So you're using a function as a value there. This is an unusual thing for us to think about and needs a little bit of wrapping your head around it, but that's exactly what's going on there. We'll use it to create animations too. When you want an animation, you're actually going to pass what you want the end result to be, which is a piece of code, size this blob up 2 times or something. You'll pass that as a function into, as a closure, into the method that then takes care of actually animating smoothly towards that end state. So we'll use this a lot. And in fact, Swift UI, which we'll get to towards the end of this class, uses closures all the time, everywhere. Right? Your whole code, essentially, building your entire user interface, your hierarchy of widgets in Swift UI is actually just a whole bunch of closures nested inside each other. Nice catch. All right. So, however, the syntax of closures can be a little tricky to understand. So let's start just with a function, okay? So here we have a function. A function has a name, like sum here, for example. It's got parameters, maybe or maybe not, right? In this case, we've got a couple of parameters. We see that it has an int array of numbers. And this one also has a return type. Again, that's also optional. We're returning int here. And then it has some code, right? What it's supposed to be doing. In this case, just a single line. So that we all know, right? This is clear. This is a closure. In fact, it's more than a closure. It's a closure, and we're assigning the closure to a variable, just to show you that this is possible, right? So the closure is actually the stuff here between the curly braces. It's a block of code, right? It's a function without a name. Again, it's a function that, as we can see here, takes an integer array of numbers. That's the parameters inside these round parentheses here. And then it has a return type of int. And then comes the keyword in. And that's a good indicator that you're dealing with a closure. We don't always see this. It can actually be left out in certain compact ways of writing closures. But if you see a word in, you know you're looking at a closure for sure. And then comes the code that makes up the closure, return total. And that's the closing brace, not of the let statement, right? But actually of this block of code that makes up the closure. And so we've defined here a function. We haven't given it a name, but we've defined a function that takes it in an array of integers and that returns an int, and that basically does that with some, we've left out the code that actually adds up the number, but it does something to it and then returns that number. And then we've taken this block of code and assigned it to a variable. So this is different from having a function with that name, right? We now have a variable that actually has some code inside it. So when you want to read it, I sometimes use this to make it clear to myself why it says in here. You could say, well, this closure uses these parameters like the int array of numbers, and it uses an int return value in the following code. And that's how you can imagine. It's my personal way of reading it. In the following code, how you can imagine why it says in there in this point. Now what we're doing here is we're assigning the closure to a constant, and that's actually in practice not very common. This is not a very common use case. So I just did it here to show you that you can do this with a closure as a bunch of data. What you'll mostly do is you'll pass closures as arguments into other methods, right? That's the typical use. Now, let's take a look at what closures can look like. Like a closure, like all values in Swift, closures have a type. What's the type of a closure? Well, the type of a closure is actually the combination of its parameter list and its return type. So you could say, sometimes people think of this as a signature, right? So in this first one here, both the parameter list and the return type are empty, right? There is nothing. And this is a print, we call this thing print closure, right? But the closure is just this bit of code that takes no parameters, has no return type, and that just issues a print statement, okay? Here, and of course you couldn't execute this in sequence because we have a let constant, so I couldn't change what's inside that, but so assume this is a different piece of code, not running right after this. We have a closure that does take parameters, but has no return value, right? So this one is a closure that takes a string, called string as parameter, and has no return types, and it prints out the string. And we assign that again to a let constant here. And here finally we have the full-blown version. Here we have a closure that takes two parameters, min value and max value, both integers, and it has a return type of integer, and then does something with that and returns that, returns maybe a random number, for example, between min value and max value. And again, we assign that here to a variable, but that's just for illustrative purposes. Now, as I said, we often pass closures as arguments, right? So let's take a look at an example of this. Collections use closures as arguments a lot. So let's say we're writing a music player app, okay? You want to basically sort the tracks that this music player is displaying. Now, we have an array. Let's assume we have an array of tracks, and we want to sort this. The nice thing is the array function sorted by actually takes a closure as its argument. So the closure is passed into the sort function and then decides how the sorting happens. So as you can see here, what we could do inside our music player app code, if we had this array of tracks already, right? Let's assume this exists. We could pass it sorted by. We could pass it a closure, right? So notice how we are calling the track sorted method here, and this is where your brain is going to start getting twisted up. We're calling it with the first parameter called with the parameter named by, and the value of that first parameter is this curly brace piece of code, right? And that piece of code, or this closure, I should rather say, is an unnamed function that takes two tracks, returns a Boolean, and what does it return? Well, it returns true or false based on whether the first track number is smaller than, less than the second track number. Okay? Let's say track number, I'm assuming here, is an integer. We can do a simple comparison on those. Okay? So what have I just done? I've told in my application code, I've said, I would like my tracks sorted by number. How do I do that? I call the sorted function on the tracks array, and I tell it what comparison function to use to do the sorting. We didn't define the sorting algorithm here, right? This is not whatever it's using, bubble sort or quick sort. I don't care, right? It's doing something, but what it needs to do the sorting is a comparison function to know how to compare two items, right? That's all it needs to do sorting. And that's what we provide, and we provide it in the form of a closure. All right, so track number, of course, you could be replaced by something else, but I could have it also sorted by maybe the track title, and then it would use the title's less than relationship defined on strings to do the sorting, or by star rating. I could change that here. And the beauty of that is that I can always use the same sorted function on the array just by providing it with different functionality. So you can see here, even in this first example, how closures are for functionality similar to what you can do with variable values for normal data, right? I can have a variable and it can have all sorts of different values depending on what it needs to be. And a closure is a piece of code, or is a function, a nameless function, and it can also have a variety of different values. So that's what we're doing here. Okay, so this is probably understandable. Now, the next little head twist that took me a while to process is trailing closures. Because this is a design feature of Swift that it tries to make the code as readable and compact when you look at it as possible. But that means that there's a lot of simplifications that will look weird to you when you first see them as a beginning Swift programmer. Once you've gotten used to it, once you're an expert Swift programmer, you will write them themselves this way because they are super easy and elegant to read and write. But in the beginning, it'll take some mental processing to understand what's going on. Because so far, maybe this is still something you feel comfortable with because, hey, we're calling a function, there's a round parenthesis here and there's a round parenthesis here. So I know the stuff in between is arguments. Yeah, one argument is kind of weird. It's a piece of code, but I can deal with that. But now, this is trailing closure syntax. If your closure is the final argument in a method, right? So the final argument that you're passing into a method is a closure. Then you can actually pull the closure outside the parentheses. And you can drop the parameter name too. Because again, Swift can derive that. And if it's the only parameter, you can even drop the parentheses completely because they would be empty. Okay, so that's what's going on here now. And this starts looking really weird probably to you because here we're calling now the sorted function. But since it only has one argument, and that argument is a closure, so it's also the final argument obviously, we can actually drop the round parentheses and we start immediately by specifying the closure itself. So that looks strange, doesn't it? That does look strange. It doesn't no longer look like a function call as you're used to from your last whatever 5 years of or 10 years of coding that you're used to. So this is something to be very aware of. So we've taken 2 steps here, right? We've said it's the last argument, so we've moved it outside the parentheses, and I could have still left the empty parentheses here after sorted if I wanted to, just to make it more readable. But in fact, I can drop these 2, and Swift often does this, and Swift programmers often do it, and Swift sample code and libraries often do it this way. We use trailing closure syntax, in which the way I think about it is I'm almost replacing the round parentheses in which I was passing normal parameters with curly braces, which are now the function parameters, right? They are the code parameter that I'm passing into a method. All right, so this is how I like to think about it. It goes from here to here, but we're using now curly braces to basically delineate where the closure starts and ends that we're passing in as an argument. All right, but we can do better. And again, it's because Swift, the compiler, is pretty smart, so it can figure a lot of things out. So for example, it will know that the sorted function, the sorted by function to be precise, it will know exactly what it expects. It will know what kind of parameter types, for example, it expects, what type its parameters need to be, right? So it knows that it's expecting a closure that takes 2 tracks of type track and passes out a Boolean, right? It knows this. This is the only way that a sorted by closure would actually be legit, right? It has to take 2 tracks and pass back a Boolean deciding which one is the smaller one. So we can actually drop the track type from the parameters. So we can say this, right? Sorted with the 2 parameters, first track, second track. Again, still the word in here. And as you can see, I've also dropped the bool return type specification. Because they are obvious. Swift can derive these, so I don't need to write them. All right, but we can do better. Since we actually we have these two these two parameter names here, we can use placeholders for these. We don't actually need to name these. And for small closures, it's just unnecessary writing to give these a name and then use it in a single line of code. It's kind of boring and unnecessary writing effort. So we can drop them, and by default, the two parameters that are going in there, again, sorted knows that it's getting two parameters in the closure, right? So the compiler knows this, are called $0, $1, etc., right, for more parameters. Now, what's the advantage of this? You don't need to specify the parameters at all. See? So we've got track sorted, curly brace. We don't specify the parameters anymore because we know there are two, and we have names for them, $0, $1. So we can start with our code immediately. And this is what I said. At this point, the in disappears as well. We don't need to write that anymore. So anytime you see in, it's a closure, but not anytime you see a closure, there's an in. Okay. So this is already now shrinking down to a single line here, right? That's pretty elegant. And then there's something else that you've probably seen before, because we can do better, right? Single line return statements don't need the word return. Okay? So now, look at this line. This is saying exactly what we were saying up there. But it's so compressed that I think it does two things. First of all, it messes with your brain as a beginning developer, right? Because this is like, what? But secondly, once you get used to this writing style, it becomes incredibly elegant because it's actually saying pretty much what we want to say. It says, I want my track sorted by the rule whether the first track number is smaller than the second track number. So if you know how to read this, it's super elegant. It's actually much easier to parse visually if you're reading code than all this, right? There's a lot of extra noise in there. We're introducing parameter names that we're going to use in the next line and only in the next line, so it's kind of superfluous. So this is what you can do, right? So you can bring this down to the single line, and that is actually not unusual at all to do. Finally, now this would not work with only what we have here, but let's assume that you actually made your track data structure comparable. Let's say you specified what it means for one track to be less than another. So for example, you have a definition of a static function less than, that's already there. Then you can also just pass in this operator. Right? And that we've seen before. Right? You can pass this in, we've done that before. You can sort an array with the less than operator. And that would work if it was already defined somewhere else. All right. So let's look at how Swift uses these things in a couple examples. So here is an example of, let's say I have an array of first names right here, and I want to create an array of full names. And this is the Smith family, so they all need the word, the last name Smith appended to their name. Okay. This is probably how you would have written this yesterday, right? Or maybe 2 weeks ago before you heard about what you can do. How would you do this more elegantly? Yeah. Exactly, right? So you would use the map filter reduce pattern, and you would use map by simply having it return the stuff in here, right? So and that is actually using trailing closure syntax and all of this stuff. This becomes really elegant. If you see this here, we're using let full names be first names, on which we can apply the map method, right? And the map method needs a closure as argument. It needs to be told, okay, what's the thing I'm supposed to do on each element, remember? And that is a piece of code. So we're passing it in, we're telling it it's a name, returning a string, and then it returns the name plus the appended, empty space plus Smith on it. Can we do shorter than this? Yeah? Yeah, you. Yeah. Exactly, right? So we could do it this way. We don't need to actually name the parameter name and then use it on the next line. We could just say, well, the thing that I'm getting, just attach Smith to it, right? For each element in the array, right? Okay, so I think as you can see from these examples, map and similar functions like filter use closures quite heavily. Let's take a look at another example. So here we have an array of numbers, and we want another array that is initially empty, but it's only supposed to contain the numbers less than 20. Right? Again, this is the old you writing that code, right? Doing a little for loop and going around and looking at each element, and if it's less than 20, I put it into the new array. That's how I would have done it before I heard about filter, exactly, right? So we've got numbers less than 20 is numbers.filter. We apply the filter, which again takes a trailing closure syntax, and it takes a closure, in this case in trailing closure syntax. We're passing in a number, it returns a bool, which basically says is the number less than 20 or not, right? And if that's true, this is how filter works. It needs a function that for each element says yes or no, goes in there or doesn't, stays in the filter or gets dropped, and then we're done. And of course, this can again be simplified further. I think it's clear at this point by using the $0 parameter here. So this is basically the numbers array filtered by the rule is the element less than 20. So I think this also illustrates quite nicely how easy this is to read if you know how to read it, right? All right. Last example. We got our array here. We're going to sum up the array. This is how you would have done it before knowing about closures and the whole concept. What do we need here? Reduce, exactly, right? So we use reduce, numbers dot reduce. So these are all things you call on the array, right? And reduce needs to know what initial value to start with, right? And then it needs to actually get two things, right? It gets an initial value, and it gets, in trailing closure syntax here, a function what to do with that value for each element as it goes through. This is a nice illustration of an example of a function that has both a normal parameter, the initial value, which is 0 here, and a closure parameter, right? So we can still use trailing closure syntax because the closure is the last argument in the parameter list, but we cannot drop the parameters list completely because obviously the other parameter needs to go somewhere. So we still have the parentheses here. Okay, and of course this can be shortened as well. This is how you would write it with, using $0, $1 commands here. And I bet you right now you're all like going, yeah, sure. But if I showed you this line of code, like tomorrow at 3 a.m., you'd be like, what? Right? So this can be confusing because all of a sudden, these normal parameters and these closure parameters are getting mixed into each other, and it looks like something is missing or somebody, made a mistake. So that's something to be aware of. In fact, you could actually do better than that because remember, whenever you're passing in a closure, you could also just pass in a function instead, right? A closure is a function. So that is the same. Because $0 plus $1 is code, right? It's a function. And that function is the same as the plus operator for integer values. And so you could actually write it like this. Like numbers reduce with starting value 0 and with the plus operator. Yeah?
Would that work for strings? Because dictionary isn't...
No, not if it's not defined. Not if it's not defined. The operator needs somewhere to be defined, of course, so that you could use the operator here.
But string addition is defined. I'm just confused because the order matters in that case for strings. Like if you add 0 plus 1,
yeah.
you get a different string to 1 plus 0.
Yeah, that's a good point. You mean like if you define string addition as concatenation, exactly. Right? Yeah. You could do that. It would probably just use the default operation for this. Yeah, that should work. But you're right. Yeah, normally the operator, the plus operator, needs to be mutable. What is it? Commutable? I think it's commutative, something like that. All right. Another thing about closures, and this is also going to be messing with your idea of scope a little, like how you understand scope. Normally, you know where a variable is visible and where you can use it, and where other, you can use the same variable name in different scopes, and they overlay each other correctly, etc. But closures, since they are pieces of code, for example, this here is an example of calling the animate method in trailing closure syntax with a single argument of a closure. And as you can see here, it's using stuff that hasn't been defined inside the closure. It's actually been defined outside. So this is often necessary because the closure obviously needs to work with the stuff that is around it. So anything that is in scope when the closure is created is actually also in scope inside the closure. So here we can access things like the view of the self object here and the background color. We can do this. So Swift basically lets closures use any surrounding constants and lets them use and also modify any surrounding variables safely inside the closure. So if we did this animation, which is going to take some time, right? Animations run over time. What would happen if the view property was actually removed from the screen during this animation? It's a little bit of a more advanced question, yeah.
It would stay in memory, but the follow would change with its own.
So it would stick around until the actual animation is done, exactly. So what Swift basically wants to make sure is that the owner of the view property must also be kept in memory as long as the animation is running, until it's actually complete. So that's also why we need the self keyword here. Normally you wouldn't necessarily need this, right? Self is usually unnecessary because you are already in an object context, but inside closures it's required to make it very clear that we are referring to the object that is in the environment of the closure. Okay, so if this is what would happen there. All right, we're going to take a quick look at animations next, because I promised you a couple of applications of closures, and animations are the next one that we're going to look at. And animations are also super useful when you want to create an interface that feels natural and smooth and that has good usability. Animations often make a lot of sense. Can you give me some examples of animations happening in the user interface of mobile apps that you're using every day? Everybody's got an example of an animation. Yeah.
For example, when you're in the Photos app and you scroll down and then you close that photo, it gets small and back to the grid.
Yeah, exactly. So you got your photo in full size and you want to go back to the overview. It kind of shrinks down into a small icon, right? Exactly. That's one example. Other examples? Yeah.
If you're in some sort of navigation view, it always swipes like in the view and out of the view in iOS.
Exactly, right? The swipe in from the side, back and forth, is also a typical animation. Any others?
I mean, just to say, unlock my mobile phone, like when I swipe up and all the icons like get to the places.
Yeah, they zoom in like that, right? Yeah. So they get placed. So it's interesting what these animations are doing, right? They're when you think back to designing interactive systems 1, if you've heard that or if you're currently hearing that in parallel, we've talked a lot about feedback, right? And giving the user feedback about the current state of a UI, what they've just done, the results of their actions. Things like this are often really shown well by using an animation. So for example, when you say you unlock your phone and these things come flying in and land, that's a much more comfortable way to understand what the phone is doing rather than the phone just suddenly showing you the start screen with these icons. And then you're like, where did these come from? Right? Some part of your reptile brain is like, that wasn't there a second before, so where is this coming from? And so these animations basically tie together the discrete states of a user interface to make sense to us humans. Because in the real world, things don't appear suddenly. They don't disappear suddenly, right? That's magic. It doesn't normally happen. So the way that animations are being used helps us to understand user interfaces better on a very basic biological foundation. So we'll take a very brief look at animations here just to show you what UI view, the mother of all visible things in your user interface, of all the structs that are available, and all the classes, sorry, what it supports in terms of animations. And we'll see how you use closures to do these animations. So there'll, again, be more about this in the seminar. So animations transition from one state to another, and this can actually be used also to sort of define how your app feels. Let me show you this little clip here. Let's say these are two apps, right, that show a bunch of things, maybe reminder lists or something, and you now want to add something. And let's look at the animation that each of them is using. Yeah. So what's your impression on, let's say, the left one? Yeah.
I think the left one is like quite playful and not
right.
that formal, I would say.
Exactly.
And the right one, I would say, it's like a form, like being serious about something.
Exactly. So the left one is like, oh, look at the new item hopping in there, landing. So it's trying to be playful, maybe more enjoyable, more entertaining, but also, as you say, less serious, less professional, less business-like, right? So the way that you use animation, and these were both animations, right? Both used animations, but one used one that was very serene and formal and simple, and the other one was a little bit more over the top. I could also imagine that this could drive me nuts very quickly if I had to look at this again and again and again for something I'm using very frequently. But for an occasional effect, this could actually be a lot of fun. So animations can define this character of an app, as I said, and they also direct the user's attention. Pay close attention to what's happening on the screen here. Okay, so this didn't just appear, right? It actually, what did it do? Yeah, it popped out, right? And it actually did that almost like a little bit of a bounce effect was there, right? So it comes in, goes a little smaller again, and then it lands. And this is a spring-loaded effect. These are given to you by the iOS SDK. And again, they help you to make these things appear a little bit more realistic, a little bit more physical, right? Rather than just being pixels on a screen. Here's another example. You said, in navigation views, when we move left and right, it helps us, basically understand where we are. Here's another example of this. We're currently in the overview of a whole year here, and if I now want to go to the to 1 month view here, then what will happen is that it actually has an animation zooming that in, right? And this is subtle, right? And from there, as you can see, we go in further to get to like a week or day view and out again towards the month and the year view. And this is subtle. You might say, oh, I could do without this. But if you ever see an interface that doesn't do this, you can immediately tell that you will feel, well, disoriented is maybe a big word, but you will feel like there's a disconnect in the interaction, right? You're like, wait, did I really tap the right month here? Or did I maybe miss it by like, a fraction and tap the wrong one? So these really help people feel more comfortable, more secure, and competent when they're using applications. So it's not just eye candy. That's what I'm trying to explain here. Final example is that these things also connect to user behavior. So some things that you're doing on your smartphone may suggest that there should be some kind of animation. And if that's done well, it'll really tell you something about what to expect from the UI and how to, for example, get back to an earlier state. Here's an example. When we play this, we're looking at this calendar view, and then something moves in, right? So pulling down the notification view, and we know that by doing this, since it's following our finger, we know, okay, if I want to get rid of it, it's perfectly clear how to do that. Just push it back up, right? So all of this is happening via animations. So as I said, we're going to look at a very simple example of how you can put animations into your user interface. It's really surprisingly easy and a lot of fun to play with these. You could also go hardcore and use the core animation framework. The core animation framework is the underlying framework that does all these things. But we'll start by using higher level standard animations that are defined for the views, for UI view, and that are using core animations functionality. If you want to see more about this, you can look into the UI view documentation. It will tell you what kind of effects you can use here. Maybe one thing that is also new at this point here, so far, we've created user interfaces in Interface Builder, right? When you've put together an interface for an iOS app, you've assembled it in Interface Builder. Maybe you've used outlets and actions to connect to stuff. Here, we're now looking at something that we need to specify in code, right? I need to actually say, I want to use this animation with these parameters to move from this to this state. So we're going to see that you're building part of your user interface in code. And again, these kinds of things need to be done dynamically at runtime. So that's why we end up writing code about them. So here are a couple animation methods that UIView provides to update a property with an animation. So you could change a property of a view, for example, its size or its color or its position, and it would immediately change, right, directly. But if you want this to happen in an animated way so that it gradually moves to this target value, then you use an animation. And what's weird about this is what you would maybe think is that, okay, I'm going to set the value and then I'm going to tell it some option to do it in an animated style. But this is not how things work, right? Instead, what you do is actually you say, I want to animate something on this view. And then what you provide as a parameter, surprise, as a closure, is the actual thing that is supposed to be the end state, right? So you say, for example, I need this view to be twice the original size in the end, and this is the piece of code that you give to the animation method. So animate takes closures to set the target value, right? And then the animate method, actually does the animation towards that value. We're going to use trailing closures here for elegance and brevity in writing this. So here's a very simple example. I can tell anything, any UI view, I could tell it to animate with a duration of 2 seconds, the effect of becoming, mostly transparent, right? Setting the alpha value to 0.3. So that's the code, right? That's trailing closure syntax happening here. There's also still another parameter that we're supplying. So the round parentheses are also still there. And then over the course of 2 seconds, the view would fade to 30% transparency or opaqueness. Here's another example. If we wanted to get a little bit fancier, right? This was the first one, right? Just using with duration, and then I provided the animations. And you noticed that in this first example, I could actually leave out the word animation here, right? So this first one doesn't actually have the word animations here because it's trailing closure syntax, so I can drop the parameter name, right? If I do it with if I do a little bit more of a complex one, I can use with duration, animations, and completion. And for completion, I'm going to use trailing closure syntax, so I can drop that name. But what you see here is now I have an animation of a view that first, over a time of 1 second, goes to being at an alpha level of 1.0. And then after that, there's a completion closure that actually, over another second, fades to alpha value 0.0. And this, I admit, this is hard to parse visually, right? This looks pretty ugly visually, but this is when you have to supply multiple animations that actually need to be happening one after the other, right? There are more methods here. So for example, the third method is one that actually lets you, I'm not going to show you examples for these. You can check out the textbook if you want to see more examples. But this adds a delay before the animation even starts, right? Plus, you can provide a bunch of options. things like repeat this animation a couple times, or maybe even indefinitely until the user or something else happens and the view gets removed. And the final one here is one for the physical modeling fans here. You can actually, when we talked about the springiness, the bouncy, spring effect, you can actually specify that in this last version of the animate call. So you provide a spring value here with a damping. You may know that springs are defined, among other things, through their damping factor, like how much do they come back, how quickly do they, and how energetically do they bounce back. And the initial velocity of the spring can be provided, and then the other things that we've already seen before. So that's how you can provide your own sort of bouncy effects here. The last one, I showed you a bunch of properties earlier on of the view that you could work with, like alpha, transparency, or size, or colors, and that one of them in there was transform. So this is for the math heads among you, because a transform, the transform property is essentially an affine transformation. An affine transform is essentially a 3x3 matrix that defines where each point goes after the transformation, right? So it takes, from an untransformed view, it takes you to a transformed view. And iOS, thankfully, you don't have to do all the math yourself, provides helpful standard initializers for these transforms. So for example, if you want to scale something up, you can initialize the affine transform matrix so that it basically defines an x and y scale factor. Or you can get a transformation matrix set up that automatically rotates a view by a certain degree. Or you can have it set up so that it translates something by a certain point in x and y. So these you can use in order to do more complex custom animations if you so choose. You can actually even combine these. You can actually say, and that's the beauty of matrices. Remember, all that linear algebra that you did in your undergraduate studies, it wasn't for nothing, right? So you can have two transformation matrices, one that scales and one that rotates, and you can just concatenate them, and that will basically then do both of these things. So the resulting matrix will do both of these things at the same time in parallel to every point in the plane. What I don't have on the slides here, but what's also possible is you can also transform or animate, I should say, constraints. Because what we've done so far is we've taken a view and we've said, hey, view, I would like you to have this cool animation effect, right, as you move from here to there, let's say. But what if that view was, let's say, part of your complete view? Let's say it's a message field that you want to gradually expand to be 50% of your overall field rather than just this line at the bottom, right? So your message field needs to grow, but this other thing, your main view, your main text entry field also needs to shrink, right? And so for that, it makes more sense to actually go in and animate constraints. Constraints on views so that all the siblings that are also depending on each other's size and position will animate along with them. And when you do that, you'll actually be using something similar to the outlets we've already seen, because then you need to connect to the constraints in IB, in Interface Builder, and you'll have to use those in code through IB outlets so that you can make a constraint animate smoothly. In practice, don't overdo it, right? So don't over-animate your interface. It will become too annoying quickly. So use it judiciously. And what you want to strive for is sort of a somewhat realistic behavior, realism in behavior, and credible behavior. So for example, if the user has to swipe down to make something appear, well, make him swipe up to make it disappear, right? That makes perfect sense. Don't make them swipe left to make it disappear then. And when you use animations, use realistic ones. So for example, let's say you've got a, when a car stops, right? The car doesn't just go from velocity, 50 to velocity 0 like this, right? That's not how it works. But if you just moved a car with a simple move transformation here from A to B, that's exactly what you would get. So you would need an ease in and an ease out, which is what these things are called, that basically slows down the velocity of movement as it arrives at its destination. Right? So you want, this is where you can fine tune to really make these things feel perfectly realistic. And that's, I think, going back to the spinner for date setting, right? They just nailed this, right? It really feels like you're spinning a physical wheel. Finally, there are accessibility issues with animation. Some people don't deal well with animations in the user interface because it throws them off. And so there are options in iOS that let people turn off animations in the UI. So you should make sure that you follow those things and respect those settings when you use animations. Let's continue with the last topic that I promised you for today, working with the web. So bringing all these things together, closures, and the way to store things persistently in code, the Codal protocol, to actually put stuff not just on the user's device, but actually being able to access data online, which of course pretty much all apps these days need to do. So let's very briefly review how the web works. You're all aware of URLs, but maybe you haven't quite taken the detailed look at what's in there. Of course, if you access any stuff on the web, you need a URL. So what does it consist of? Well, there's a protocol, which is usually HTTP or HTTPS these days, but it could be something else. Then there is the domain, which is something like apple.com, plus possibly in front of that the subdomain, right, like iTunes in this case. Then you've got a path, which looks like a Unix path to a file. And then after the question mark, you may have query parameters that go in there. And these query parameters are a lot like dictionaries in Swift. Like they basically have key value coding, right? In this case, it's MT is set to 12, for example. So ports are missing from what I'm listing here, but that's just because both HTTP and HTTPS have default ports that all servers are usually using, 80 for HTTP and 443 for HTTPS, and web browsers just check for those ports first, so they don't need to be specified. Although you can if you want to. So the URL is the most important part in a request when you send out a request for data, but it's not the only part, right? What's also in a request that gets sent out to the web by a browser, for example, is the request type. The most common ones are GET, when I'm asking for some information from, for example, the web page, or POST, which is, for example, what you use when you have a form where you enter some data and then send it off to the server to use. And the next thing that's also in a request is headers. These you don't usually see as an end user because they're not necessary for the interaction for the end user, but they are also part of the request. One example is the user agent. The user agent very detailedly specifies what kind of browser or client made that request. Was it Mozilla in this version X or whatever. Authentication and cookies are also inside these headers that are usually invisible to the end user. And then finally, of course, there is the body, right? When you have HTML, CSS, images, JSON. For example, responses also have headers, like expiration dates or of the return data. And of course, they also have bodies that are sending back. Okay, so what we need to build, of course, to make a request is a URL, right? So when you want to create a URL, it's not hard. There's actually a nice way to do this. There's a data type called URL, and it has an initializer that you just pass a string into. The only thing that might throw you off here is the forced unwrapping here that we're doing, because that's like, ooh, nasty, right? Well, the point is this can fail, but this has nothing to do whether the server is actually online or anything like that. This has only to do with the fact whether the string that you're passing in contains any invalid characters that couldn't be part of a URL. So as long as you're sure of that, and in this case, I'm pretty sure those characters are all valid characters for a URL, you can, in this case, force unwrap. However, if you did this URL thing here, you could probably, for example, go in, and this URL data type has properties like the host property, and you could get a hold of the host to see, for example, the apple.com domain being listed. That's possible. But what we need to do with this URL is now to actually ask the web to, ask the server that we're addressing here to give us back some data. Now, for the moment, I would like you to ignore this whole task wrapping that we're doing here, right? Let's just start with looking at this first line here. So let data response has a couple interesting things. It actually takes a tuple as a return value, right? So we see that this call here, URL session shared data, actually returns a tuple. It fills in both the data and it fills in what's called a response. The response, as we can see later on here, we use and we interpret it as an HTTP URL response, and only if the status code in that data type is 200, which means OK from the web server, then we actually try to read the data as a string encoded in UTF-8 standard form and create a string by using this initializer and then print it out. So what this would do is basically go out, try to get the data from this website, from the homepage from Apple, and it would get back a whole bunch of stuff, and it would interpret that as a textual string data and would print it out if it was successful. Not very useful, but that's what this does. So URL session here that we're using is a class that you use to build and run network requests. And it's a shared instance here, as you can see, that we're using, because that is one that you can use that's already provided for you, and it manages all your network requests. You can create your own, but we're not going to go into that much of detail. The nice thing about this URL session shared here is that it is where you can basically, it will manage your network requests for you, and you can tell it what code to run when certain requests complete, when they actually come back. So we start basically by requesting the data from the URL, right? This is what this thing does. It takes a URL and gives me back the data. So that's basically a one-liner. Sounds very simple. And then basically we print it out. The bag of bits that data returns, right? This is just an unstructured bit stream, is turned into a string here by using the initializer. But there's a couple things that are a bit tricky here, right? The URL session shared data call is actually an asynchronous method. And that makes perfect sense, right? You want this to be asynchronous because this could actually take a while until the web server responds with all the data. And while that's going on, you don't want your complete app to freeze, right? You want the user to be at least able to continue to interact with your application and maybe do other stuff, maybe update the other parts of the UI, maybe show a progress bar, whatever. So it has to be an asynchronous call. It cannot happen in a simple synchronous call. So we're dealing with concurrency here. And we're not going to go into details on concurrency here today, but this is going to serve as a first example of a simple case here. So we cannot block the main thread on our app, or as Swift calls them, the main actor, which is the one that is managing our UI and keeps it running and looks for input from the user and responds accordingly. We have to be running asynchronously from that. Any methods that are asynchronous are then called with await. Await basically says inside this asynchronous method, this is where execution could pause until this thing actually comes back, right? This is sort of the marker for the compiler to understand where it could actually stop or pause execution until the rest returns. The other thing that's interesting about this call is that data is also a method that could throw. So that's why we need to wrap it into a try here at this point. And the task is a structure that we put as a whole around this whole thing so that it can actually have a context in which to execute this asynchronous request. And since data itself can throw, task itself could also actually throw. So it's a little bit more involved, right? This whole task wrapping is necessary because we're dealing with an asynchronous request. There are other ways to do this. You could also have said that this whole block of code here is asynchronous itself, But then you'd have to still deal with that issue at some higher level of processing. So when we do this, what do we get back? Something like this. So maybe not the super most useful thing to see. It will actually be even longer than what you have here. So most times when you're writing an app, fetching HTML-based web pages is probably not what you're actually interested in. What you're interested in is usually in an iOS app or any mobile app to get some raw information, and that is typically structured in something like JSON. And then you serialize that JSON information and turn it into objects of your model in your MVC paradigm speaking. And then you show those things. Right? That's what you're typically interested in when your apps are talking to the web, not when you're browsing the web, but when you're working with applications that talk to servers. This is what you do. So how does that work? Well, it works using web APIs. And web APIs are kind of similar to what you have as APIs in, UIKit, for example, right? It's simply a certain protocol in which you can talk to a server. It tells you what kind of requests you can send. It will tell you what kind of things you have to expect back, what can fail, what is optional, et cetera, et cetera. So as an example here, we will use NASA's API for the picture of the day. So NASA every day posts a picture that's from some astronomy telescope. It looks always awesome and has some explanatory text going with it. They do this every day, but they don't just publish this website. They also provide an API so that you can write an app that directly gets that image, that directly gets that text back, and then you can do your own things with it. So you can write your own picture of the day app. You don't have to get the HTML from the NASA website and then reverse engineer and parse yourself through the HTML, and because that would break the moment that NASA changes their website, right? The way if they change the title, your parsing might fail. So that's like the ugliest way of getting data off the web, right? By parsing HTML websites, web pages. We don't want to do that. We want to talk to APIs if they're available. And you can go to api.nasa.gov, and then there's a listing for how the picture of the day, APOD, API works, and it explains to you what to expect there. And so what do we do with this? Well, we learn from this that, like many websites, the APOD API uses what's called an API key. An API key is usually a secret thing that you as an app have to have in order for you to be allowed to talk to the website's API. Because you're using their resources, right? You're using NASA's compute cycles when you're asking for these pictures. And so if your app does this 1,000 times a minute or so, then NASA's not going to be happy. So that's why, like many web APIs, NASA uses an API key. But they also understand that people don't always want to go through the hassle of applying for an individual key, blah, blah, blah. So there is a shared demo key that you can use to start getting access to this page, right? So this demo key goes into your URL request that you send off. And the demo key has certain restrictions. For example, it only lets you, I think, fetch 50 images a day. After that, you get an error from the API. So turn off your auto run, if you're doing Xcode Playgrounds, turn off the auto run, because otherwise you'll be, you will have ruined your daily allotment of pictures after just a few minutes of compiling. Alternatively, you can, NASA gives you a free key that you can ask for, and it doesn't cost anything. It's mostly there to control what people are doing and to be able to trace back who is requesting something weird. So that's the only idea behind it. First of all, this is very similar code to what we've already seen. It's just another URL we're plugging in here with this demo key attached as an add-on, right? And you can leave out the date here too. If you don't want to provide that, then you get the image from today's date. And if we do it with this kind of request, then the response would look kind of like what we see down here. So that's better than what we saw before, right? This is not HTML, just as plain text. This is actually a structured JSON data structure, right? So we can actually see what we're getting here is essentially key value pairs of strings, right? Date, explanation, HTURL, media type, service, version title, and URL. So that looks pretty useful. you can also send this request not the way that I just described, where you hard code everything into the URL string, because maybe the user wants to, pick their own date that they want to get the image from, right, in your app. So then you stop using hard-coded strings, and instead you provide individual items. For example, you can set the API key to be demo key. You can set the date to be something, and that makes it, accessible to you as a programmer to basically provide your own parts to assemble the URL. So you could have a date picker. The user picks a NASA image date, and then your app goes out and gets that. And again, we're not simply using string functions here to assemble these things. We're actually using URL components and URL query item as functions that the Foundation framework provides to us to do the right thing. For example, a space cannot be inside a URL. As you all know, it has to be turned into a %20. And so that we don't have to deal with this, we've got these functions that do this. And we also see an interesting little application of the map function here. Just want to show you what's going on here. So we've got the API key and demo key and date 2013 and so on. So we've got two key value pair strings here, or key value pairs that are both strings. And what we're doing here is we're taking this array of string pairs, and we're applying the map function to it. And there is the trailing closure syntax closure here is that we call the URL query item initializer on it by using the key and the value of the first and only parameter that goes into each of these things. And thereby, we basically, from the array of string pairs, we create an array of URL query items, which are also dictionaries with a key and value, but not string type, but instead this special one. So that's a nice way to create the query item array from these strings. And it also shows how to use the map function nicely. And then you would use the query similarly, but you would use basically the components URL that we've just assembled now by doing this, right? So we would basically get back the corresponding result like this. Right? Here's where the components URL would then go in, and you would be able to get this stuff back. So now that takes us almost, to a finished app. We've created a URL. We've requested the data with the correct API keys. This is what we want to get at the end, right? This is where we're heading for. Now we need to think about how to create a Swift model, decode the JSON, and update the UI. Right? So the first two things are done. The next three things are still left to do. So these are the things that we need to do to ultimately get to the working app that displays that. And how to create a working Swift model and how to decode the JSON and update the UI is something that we'll cover in the next class. Okay. So with that, I'd like to wrap up. We've seen a bunch of things today. We've looked at closures. We've looked at how they apply in animation. We've seen how we can store data, encode and decode, and we've started working with the web to fetch stuff. Thanks very much. See you next time.
This content was provided by RWTH Aachen University.